Hi, everyone. Today I'm going to be sharing our recent work on a new system that can sense biological information from inside the ear. This is a joint work with my colleague in UC Denver and a few doctors in Children's Hospital. So Americans, or 30% of them, are suffer from sleep deprivation. Whether you know it or not, you're probably one of the 35%. And this is highly correlated to many popular disease, including depression, diabetes, heart failure, and because of this big problem, there's a lot of investment has been put into sleep study, right? And in the hospital, the way that people are studying sleep now is that they divide their sleep into 5 different stages: awake, which is obviously when you're awake, and a sleep stage N1, N2, N3, and then REM, which is the deepest sleep or rapid eye movement, right? And in order to classify these sleep stages, there are gold standard device that's called polysomnogram that capture your brain signal, your eye signal, and your muscle signal. And based on these signals, it can classify your sleep stages. For example, when you're awake, the brain signal are at a higher frequency. It's at a range of 8 to 13. And during stage 1, which is when you first start drifting into sleep, your brain is actually slowed down. But when you go to stage 2, it actually speeds up. And there's some patterns on the EEG signal, such as K-complex or spindle, where the brain signal would look like a saw-like with a very high frequency. And when you go to sleep state N3, it would be the frequency is even lower. Now, your body is really relaxed, but your muscle, your chin tone would still stay pretty stiff. Now, the deepest state of sleep, which is the most valuable sleep stages that we need, is the rapid eye movement stage, in which during your sleep, your eyes move really fast, right? And during that stage, your brainwave is of a mixed frequency. That's why you cannot use brainwave to classify your sleep stages. What doctors are now using is an eye signal and the muscle signal, because in those stages, you would have very loose chin tone. You totally relax on your face, right? So the takeaway here is not those details, but the key is for you to, or the gold standard now to do sleep study is using any ways to measure your brain signal, eye signal, and muscle signal. So what is it today? What does that device look like? This is a common picture that you would see in a hospital for a PSG. At the far corner here is a PSG. There's more than 30 sensors will be mounted on the person's body and more than 20 of them are mounted on the brain. 60 of the electrodes will be mounted on 60 as well as 16 or more of the electrode would be mounted on the head and also mounted on the eyes and muscle. Other electrodes you can see here down in the body on the leg or around some band here that measure the breathing would be used to diagnose the problem with sleep, right? So if you detect there's some problem with sleep, doctor would base on those sensors to diagnose. Now, this is what you would find out there, and I personally see this picture 3 years ago, and this is the motivation for me to go in and do this kind of work, where we were trying to reduce the number of sensors. We try to make sleep monitoring to be less obtrusive. And what you see here is a kid, right? She was around 8 years old, and she was wrapped around on her head so that all the sensors will not fall out during sleep. And now, the interesting part is, the doctor would ask her to sleep normally, for her to sleep, right? It is certainly impossible, right? Let alone the fact that now you're moving from the in-house environment for sleeping, now you move into the hospital, the temperature is different, light is different, the nurse is coming in and out, so that is the discomfort and the extra cost that you have to pay. But in addition to that, other than just uncomfortable, it takes around 30 to 45 minutes for doctor to set that up, or nurses to set that up, right? And then after the study, the result will be analyzed by well-trained expert to do classification of their sleep stages. So it is some important problem, and obviously there's a problem that we need to solve here. Can we make it less obtrusive? Can we make it lower cost? Can we make it more convenient for a patient, and especially for kids, right? So existing work are out there that try to solve such a problem. For example, there are many apps that you can find on just Apple Store or Google Play Store where you can download the sleep monitoring app. The key that's missing here is that they only use integrated sensor inside the phone. For example, microphone or accelerations or IMU. And from that, it can infer pseudo sleep stages, right? Because now you don't have access to the brain signal, eye signal, muscle signal. It's impossible for them to do accurate sleep monitoring, right? And I'm sure many of you here actually have a paper or two on that. So this is not a stranger for our community. Now, the next trend, or to address that problem, there are commercial products that try to build sensor, try to capture that signal. For example, what you see here is a device called Zio. This device is, as you can see, it need to be worn during sleep. And guess what the problem with when you have to wear something like this during sleep? It falls out. It's uncomfortable. And for us to validate, to try this out, I asked my poor graduate students that we bought a few of these and asked the student to wear this and sleep for 2 weeks, right? Just to test to see the feasibility of the device, and the accuracy is around 40 to 50%. And this is commercial device, right? It's out there. I don't think it's FDA approved, but it is so inaccurate that unfortunately the company has closed since 2012, right? So other devices are out there. For example, this mask-like device can try to monitor your brain signal when you wear, and you need to wear something like this during sleep. Or this is a device that is designed mainly not for sleep, but for monitoring your, that would help with hearing aid. So it uses a number of electrodes here to capture EEG signal. So the problem with all these solutions are, one, it's uncomfortable. Two, it is inconvenient to wear something like this when you're asleep because it will fall out. And because it can fall out, it reduces the accuracy. But those are not the key. The key here is that this device can only capture a single channel, right? And most of the time, it can only capture EEG. And because of that, the estimation is not accurate. We ask the question of, is it possible for us to build a solution that is low cost, comfortable, less obtrusive, and that's why we introduced a new system called LIBS, or lightweight, inexpensive, in-ear biological sensing system. The idea is you would have a device that is very similar to your earplug or your headphone that you wear during sleep, and because you can wear it during sleep, it can monitor all three signals that I was explaining here. Well, I will go through each challenges when we try to build this system. So the first challenge that we run into is that now, because the space inside your ear is very small, you can only mount a small number of electrodes inside. Or even if you have multiple electrodes inside, the spatial diversity doesn't allow you to measure. Even if you add more electrodes in, it doesn't work. It doesn't help because you need to diverse the space in order to amplify the volume, the voltage if you want to, right? So because of that, we only have a single electrode, and because you have a single electrode and you try to estimate three different signal and noise, right? So this problem is now you have a single source, but you want to get three signals. It is in the literature, it has been known that you can separate the source, separate the signal, if the number of the source is greater or equal than the number, if the number of channel is greater or equal than the number of source. But this is not the case, right? This is a fundamental challenge that required a new algorithm. But to make it even more complicated, all the frequency and amplitude are overlapping. So you cannot just convert it into frequency domain or based on the amplitude to split it. And even more complicated is that it is vary from person to person, and it's vary from time to time, right? So we propose a new algorithm that, based on non-metric factorization algorithm, that take advantage of a new training mechanism and in combination with this technique to split the signal out. I will give a high-level idea of the algorithm here, and I will refer the audience of interest to refer to the paper. So if you represent a signal X here as a signal as the output of our in-ear device, it will be a linear combination of three different signals, XI, SI from 1 to 3, and with different weight and a noise, right? So with metric, non-negative metric factorization, we try to factorize this into two different metrics. The spectral template metric, which is X, would, the metric W here, would be representing the invariance, or with a very little variation over time, that representing the core of the signal, and H is the activation metric that show the weight that is changes over time and register the signal at each time that express the presence of that component at that timestamp on the original signal, right? So if we know W and H, we should be able to estimate SI, right? Now, since W is a basis pattern, it doesn't change a lot over time. So, and keep in mind the a lot here. It does change a little bit, but it doesn't change a lot. So first, we try to estimate W through, I will introduce another machine learning algorithm right after this, but so if we can estimate W and using that as a starting point for us to do the separation algorithm. But assuming that you know W, and then how do you calculate H, right? Remember that in this case, we already have X as the input, as the output of our in-ear device, in-ear signal, in-ear device, right? So if we know W, we can estimate H, and we formulate this as an optimization algorithm where a good approximation of H would minimize the distance between the product of W and H to X. And we adopt an Itakura-Saito diversion measure to use it as a distance metric. And the reason for us to pick this is that it is a scale invariance metric that allows, that is not affected by the scale of the whole signal. Because every time you put the device inside your ear, depending on how you put it, how deep, or if you put it not very deep, then the amplitude or the contact point will be vary from one time to another. So the whole signal will either scale up or scale down because of that, right? So now, and we introduce and we use a multiplicative updating iterative rules to keep updating the H metric. And as I mentioned, W, we don't assume that W is fixed here. We use a known pattern W as a starting point for our optimization algorithm. And this, every time that it goes through this iteration, it will improve a W for each chunk of data that we are trying to estimate. So this is why we can, based on the core metric of that, assuming that the signal doesn't change very much, but then we would move based on the iteration here that it can improve. And the question here is, does it converge? What if it runs into the local maximal? Or what is, can we identify the number of core patterns here, right? So I refer you to all the details in the paper. And now, that is assuming that we can estimate W. So how do we estimate W, right? So W metric, or the basis pattern metric that we assume doesn't change a lot, would be estimated using single class SVM learning process that allow us to extract the support vector. But the high level idea here is that we try to seek for the hyperplane P that can separate data from the origin with maximum margin, meaning that you try to push this hyperplane as close to the data as possible so that it minimizes the margin, right? So, and by applying this, we would have the conversion is guaranteed, the local minimum problem is addressed, and it returns the number of basis pattern that is included inside the signal. Now, in short, our algorithm to solve the signal separation is we make a key contribution here in terms of removing the requirement in the number of source versus channel, right? Now we can separate signal even if the signal, even if the number of source is greater than the number of channel. And in this case, we have at least three source and the noise, and the number of channels that we have is 1, right? So this algorithm, in summary, it has 2 steps. We have a learning algorithm that will try to extract those basic patterns, and then output of that will be used during the separation process, where we would get a mixed in-ear signal, go into our iteration, and the output of this would be 3 signals, EEG, EMG, and EOG. Now, that is the first challenge, right? The second challenge coming from the fact that the human's ear is relatively small. And if you talk about kids, baby, newborn, it's even smaller, right? So, and during sleep, people move. And when they move, they create pressure, especially if you sleep on the side, you create pressure and that push the ear canal even smaller, that change the contact point, change the quality of the touch contacts, right? So this is more of a design problem than a key algorithmic problem. But I will explain how we solve this problem. But the second challenge that makes this problem even harder is that the signal that we're trying to measure is rather far away from what you normally get from the PSG, right? With a PSG or the polysomnogram that I just mentioned, you see that a number of electrodes are mounted on the skull, meaning that it's very close to the brain, for example. It's very close to the eyes, and also it's very close to the muscle. In fact, it mounts directly onto those points, right? What we are doing is relatively harder because the signal source is further. How do we do that, right? How do we address that 2 problem? First of all, we carefully pick the material so that it's deformable when you sleep, so that it's first of all comfortable. It also deform and change the shape itself, so that when you sleep, if you turn, it would change. It would be deformed caused by that force. And when the force went away, it go back to the normal shape, right? Because of that, it improved the signal a little bit. Now, that's not enough, right? Because when that surface is kept, the elastic surface would introduce the gap between the in-ear kernel and also the surface of this. So what we have here is that we need to have the material that's really conductive, highly conductive, low resistance, and flexible, durable, right? So what we use here is that we carefully crafted these 3 layers electrode. That is, just the first layer that from the bottom up, you see, this is a conductive cloth. Conductive cloth has the ability to just, well, as the name suggests, it can conduct electrical signal, right? And the second is a conductive and clinically safe gel that would allow the signal to go through here. And also the top layer is a pure silver leaf. It's really thin so that it's soft. It's also flexible. And the problem with a thin silver is that if you bend it so many times, it will break out. That's why we have this glue layer, and we glue that on top of the conductive cloth to make sure that even if you squeeze it, and in fact, for us to be able to use this, and if you're familiar with the earplug, you know that for you to be able to put it inside the ear, you have to squeeze it, right? And when you squeeze it, it will deform the electrode here. But when it expands back out, it goes back to its normal form. Okay, so that is by doing that, we have a deformable and highly sensitive sensor. Now, with that design of a system, we take the output of our system and put it into and design just a simple system for sleep classifications. There's nothing novel here on sleep stage classification, as I mentioned. It is so common in our community already, so I'll just skip all the details. The first piece that once we get the signal from the ear, we certainly need to pre-process it. Again, there's nothing novel or fundamental here. And then in the signal separation process, you would have 2 steps. One is a training that would help us to get the template matrices. And also, output of that would go into the pre-processed data from the previous steps so that we can do non-metric factorization and export 3 key signals. Now, when it go into the sleep stage classifications, we would also have the same, right? Training and classification. And this training step is take a short period of time. Well, even though I call it short period of time, it takes about an hour. And the reason for us, and the way it works is that we just set a person down for an hour and ask the person to try to sleep. Why is that? Because we want to see the whole cycle of sleep, going from awake and 1 and 2 and 3 and then going back to RAM, so that we can get all the feature that the signal should have. And then we use that for classification to estimate the sleep quality. And excuse me for some of the typo here. Now, we try to see and evaluate our system to see how well it performs in sleep stages classifying, right? So these figures show our prototype with a LIBS sensors that is, as I just mentioned, it's connected through a sealed wired and then connected to a brain-computer interface board that allow us to extract those signals. And then all the data recorded will be stored in a memory card so that we can process on our computer. And in our study, we have 8 subjects with 38 hours of sleep, and the average age is around 25. And we use a gold standard here, which is a PSG, and you see a number of wire going into the subject here. And this figure show the result of our evaluation, where the x-axis show the segment sequence number, and each segment is 30 seconds, right? And the y-axis show different stages, and this is the output of our system of our sleep stage classification. Now, these colors show the ground truth, and as you can see here, our accuracy is really high. It's around 95% of the time that we get it. The classification is similar to the PSG's output. And remember, the cost for a PSG in the hospital is ranging anywhere from 2,000 to 5,000. The device itself, the ground truth device we are using here, is a donation from a company that it costs 38,000, right? And just for the device itself. And our device should cost in order of tens of dollars, right? So, we want to see how much of the separation of the signal that help with the performance of the sleep stages classification. And to our surprise, it doesn't help a lot, right? Maximum, it helps 5%, right? So why is that? I think the reason here is that because the signal is very close to all the, it's very stable, and we can capture all 3 signals at the same time, and because those signals are relatively distinct and distinct enough that when after the training, the performance is already pretty accurate. Now, we want to see if we can really capture eye signal, brain signal, and muscle signal, right? And so we conducted an experiment where we would have a user to standing in front of a board and look to the left, look to the right, look up, and look down, which is mimicking or simulating the movement of your eyes, right? And what you can see here are the results for different eyes movement: left, up, left, right, and up, down. And the same here, the user would repeat. And what you see here is that the device can detect up, left, and right very accurately. And there is a reason for it, right? But first of all, when we look at the ground truth, even the ground truth or the polysomnogram FDA-approved device can only estimate can only capture up and down event only, and it can barely capture it can only capture left and right, but it can barely capture up and down. Why is that? That is mainly because of the structure of your eyes, because the eyeball, the back of the eye would have, it's polarized, the back and the front. If your eyes move horizontally, then because the PSG has, or the FDA-approved device, a ground truth device has electrode here, because of that, it can only see the horizontal movement. And when the movement is on the up and down, that doesn't create a lot of voltage changes, and that's why even the ground truth cannot capture it very well. And we are not able to capture it very well neither. But we can capture all the key features that the gold standard PSG can capture. Now, next is we try to evaluate if we can see muscle signal, and this would mean that we can enable other application as well if we can capture muscle, right? And I'll mention about that later. So in this example, in this study, we would have a user to wear our device and grind their teeth. And we wanted to see if we can capture that signal. Certainly on the ground truth, so these show some of the chewing behavior, or this is a grinding. Certainly grinding would have a higher amplitude, right? Because the force that you create is higher, and because of that, the muscle signal that you would send out is higher. And on our system, we also can capture that, and we can capture that very clearly, right? So next is we want to see if we can we can capture the signal on the brain. So this is these are the two experiments that we done to see if we can really stimulate the brain signal. So in this example, we would play audio and visual signal at 40 hertz. And what expected is that when you play a sound at 40 hertz, your brain would have a surge at 40 hertz. And you have visually at 40 hertz, the brain would have a surge at 40 hertz as well, which is surprising. And this is new to me when we do this study. And yes, you can see here, this is the result from our device, and this is a ground from the ground truth. What we can see is both can see the surge. The difference is the ground truth can capture with a much higher amplitude compared to our. And as I explained before, the reason is that our source is very far away from our electrode is very far away from the source, unlike the PSG where you really mount it on the skull, right? And now another experiment that we wanted to do is that we want to see if we can really see the other kind of brain wave. So what we do here is that so this is a signal, a mixed signal that we get when a person is on delta wave, which is on a certain sleep stage. So the way we extract this is we just go back to the PSG signal, find the stage where the PSG signal, label it as a sleep stage, I think N1, and then N3, and then we would extract that signal out and map that signal to the signal that we have from the LIBS, and we want to see if we can, applying our separation algorithm, can we see the signal? And the result is yes, when we separate the signal, we can really see that the appearance of that delta wave here, and also on the ground truth, you also see that the ground truth can actually capture it at a much stronger amplitude, but both systems can see it, right? And we conducted a short exit user study where we asked a number of questions to the user. Do you like it? What would you want to improve this? And these are some of the results. Interestingly, they don't like it, right? Because they don't want to wear anything to go sleep, especially when you have a number of wires. But if you remove all the wire, and if you can make the device to be wirelessly operatable, then they will be more interested, right? So there are more details will be presented or already in the paper, so please refer to the paper for more detail. So where do we go from here, right? As I mentioned, we don't just want to use this for sleep study. If you can separate three signals separately, there's many applications. So what are those? First of all, we've talked about sleep monitoring. And so far, we try to solve the problem in the hospital, but you can very well take this system home if the device is cheap, reliable, and easy to operate, which is what we have, right? We just need to improve the engineering part of it, and our goal is trying to develop this to become a platform so that other applications can be enabled, and certainly each application would have different requirement of that, for example, reliability, power consumption, etc. Right? So other possible application is seizure detection. There are many incidents or accidents happen because people are driving when they have seizure, right? So with this, if the technology is fine-tuned enough that we can capture brain signal, then we can predict when seizure would happen, so that we send an early warning. And certainly, what we have from what we have now to this application, to realizing this application, would be quite large of a gap, right? But those are the direction that we want to take this to. Other application could be driver distraction detection or drowsiness detection, because all of these you can really tell from the user's eyes, right, or from user's brain. If a person is sleepy, the brain is different. If the person is distracted, because you can localize the position of the eyes, you will know whether they're looking straight on the road when they're driving, or they're really looking at the phone, right? Unless they move the phone up here, right? So that could be the potential application. Other application including a work that we are working with a doctor in audio neural doctor, where the problem is coming from the fact that current hearing aid devices only have a steering, very simple steering mechanism. And the way it works is that a person would be wearing a steering aid and a hearing aid, and every time the hearing aid is turned on, it will try to tune to the area where the most amount of noise is created. What I'm illustrating here is, for example, this crowd. These two people are talking to each other, but the hearing aid will try to steer to this area to capture the sounds. But that's not what the user wants, right? What the user wants is, hey, I'm talking to this person, steer it back here, right? So that is the kind of application that we hope we can enable in the very near future. Other application including eating habit monitoring. Because as one of the examples that I show, now we can monitor your muscle. We know that how often you chew, I mean, assuming you're wearing, and keep in mind that we can augment this technology into existing earplug, right? Or existing headphone. Now with the headphone, with the sensor here, you can really monitor how often are you chewing, how fast are you chewing, how much are you chewing, what is the force that you're chewing. I can infer the kind of food that you're chewing, and then from that we can infer the eating habit of a person, right? And or this is an interesting application that I really like. I don't know how long it'll take for us to realize, is learnability evaluation. Let's say you have a kid and you want to understand your kid more. And so the kid doesn't talk much, right? And it's hard for you to infer what subject is the subject of interest for your kid. What is the game that the kid is interested in? And when someone doing an activity that capture their attention or of their interest, their brain is expectedly would have different patterns. So if we can enable that, we can augment learnability. And the most straightforward application that we can see is using this for wheelchair control or human-computer interaction, right? Where you can really combine eyes, brain, and muscle. Let's say if I want to go ahead, I'll go straight, I would look straight, and combining with some of the brain signal. So that certainly requires more advanced machine learning algorithm here to detect and to classify the kind of action that the person wants to send the control signal out. But that is the future of LIBS that we want to take it from here. So in conclusion, we really hope that we can build a platform out of this that open up for the community. And if you are interested in any of these, please come and talk to me after the talk. So we have, in short, right, we've developed a new platform, a new system that can measure brain signal, eye signal, and muscle signal. And the system is very lightweight, low cost, and less intrusive compared to existing PSG. And we introduced a new signal separation algorithm that addressed the problem of limited number of signals of the channel. And also, we designed and implemented a sleep staging system that evaluated on a small number of people, but it showed the feasibility of our system. With that, I would conclude my talk, and I would answer questions. Thank you very much.
Okay, any question for the speaker?
Hi, Daniel from Colombia. So
Hi.
when you compare, great talk, really good. When you compare with your system with the PSG, I guess, like the complex one, you say you can tell which stage of sleep you are.
Yes.
Is this enough for the doctor? Is this all the doctor needs to provide like diagnostic for a patient?
That's a good question. So as I mentioned, right, there are in a normal PSG system would have around more than 30 sensors. The information we provide here is enough for doctor to do sleep stages classification. Now, whenever you have a patient in the hospital, you want to not only detect the problem, but you want to identify what caused the problem. That's why they have more sensors. For example, they want to measure your breathing volume. They want to measure your leg movement so that they can tell what caused that sleep stages. But for us to do sleep stages classification, this is enough. And this is enough for the doctor to understand. Now, is that useful clinically? Yes, right? Because 50% of sleep study in hospital turn out to be false positive, meaning that you don't really have sleep problem. You go into the hospital, you pay from 2,000 to 5,000 to do a sleep study, and it turned out that you don't have any problem. So if with this low-cost system, you can use this as a screening approach, right? Why don't you try this first and then come back here? I get the result, and I'll see if I need to do an extensive one.
Thank you.
Yeah, thanks.
Thanks a lot. I have a question. Do you think that the very way you do the censoring, so you put the device inside of your ear, so you're actually occluding what you're hearing, will affect actually the study of your sleepiness?
Well, personal experience is that I prefer to be really quiet. So, I mean, that's why you see many hotels should provide you with an earplug, right? So, I think for sleep, yes, I think it doesn't affect your sleep quality. I think
maybe it improves it, but
I think so. But I agree that, and as you can see in our user study, right, it's not everybody like it. Do they against it? No. But do they like it? No. So I rather sleep without any of those plugs, right? But if the environment is noisy, especially if you're in those sleep lab, you realize that there's all kind of noise, especially the beeping sounds. And nurses come in once in a while to check up on you. And if the kid go into the study, there must be a parent go with them. So the parent make noise, or parent watch the TV, and the kid is trying to sleep. This actually helps. So that is for sleep alone. Now, for other applications that I just mentioned, for example, human-computer interaction, right? We don't really need to have something that blocks your ear. As I mentioned, you can really augment in-ear, you can augment the headphone, right? You can put the sensor on and you apply the algorithm. Certainly there would be some requirement for how you design the sensor, but I don't think that would be a problem.
Thanks.
Thanks for the question.
I actually had that same question, but I have another one, and that is, when people wake up during the middle of the night, as some do, that's one of their challenges with getting a good night's sleep.
Right.
I can imagine your sensors probably reveal a lot of different things depending on the nature of their wakefulness and whether they get up and use the restroom or something like that. Is there something you can tell about, is there enough variety in the signals during the wakeful state that you can learn something about what's going on during those periods?
We haven't looked into that. I think that's a good domain to explore. But I think, so intuitively, I would say when you really get out of the bed, in order to lift your body out of the bed, your body would generate much more significant muscle signal. So I think the muscle would be widely different, right? So the muscle would be different. I think the eye would be different. Different in the sense that now it is more movement. It's more human-like movement as opposed to sleeping REM-like, which is really fast, right? It's order of hertz, which is like we don't move it. We don't move our eyes in order of hertz, right? But so those are the signals that I think if we want to explore, we can explore that, and I think it would give us some clue about the user's behavior or user's activity during the night.
Thank you.
Thanks, David.
Hi, very nice work.
Thank you.
So one aspect I didn't catch during the presentation is if you can do the signal processing in real time, or if you need to store the signal and then when the guy wakes up, you get your instrument and you do the processing.
So I think if you want to do real time, meaning that in order of sub-millisecond, then the answer is no, because I think we need to wait for an epoch that it makes sense for us to synthesize a metric, but it should be sub-real time. It will be in order of a second or so. Now, is it important for someone to do real time? I don't think so, right? Unless you have some
in the
real
case
time
of the
controlling,
Caesar,
right?
for example.
Right. Well, Caesar, it's normally happen in order of minute or order of minute before. It
but if
happened.
I'm driving, probably
Absolutely, I agree. Yeah. The earlier the better.
But
yeah.
anyway,
Right.
So if you go back to the last slide, there's the second point where you say that you introduced a new algorithm, but it seems to me like this is a pretty much standard blind signal separation problem, and there have been for years other algorithms out there like independent component analysis, principal component analysis, singular value decomposition. Here you are just doing basically non-negative factory factorization. And in fact, your signal, it's actually, for example, independent component analysis used in this cocktail party problem. I have a lot of people
And we tried that and it
talking.
doesn't work.
All right, why?
Well, I think if you do independent component analysis, you would get a fixed components coming out of the training. If you look at the algorithm that we have here, we have a step that iteratively adjusts the W metric that allows you to really shift it from the fixed value. And so when we test that, we found that what we propose here is more robust compared to what is.
So in the paper you compared all this some other techniques? Or?
That's a good question for my student. I believe that it's not.
Right.
But I would be happy to chat offline.
Just,
but we did try that.
It's just for me when I saw a new algorithm, I was like, this is non-negative matrix factorization, and I mean it's been out there. And for example, there are also different divergence metrics. Normally, the callback library is applied. Here, I see you apply a different one.
Right.
So probably I would like to ask why you went for that one, but.
So the distance metric, the reason that we, as I explained, right, the nice thing about the Ikata, the distance metric that we applied here is that it is scale invariance. But what that means is that when you put the earplug inside the ear, you can put it really deep and tight so that you have really good contact point. Some other time you would put in and it's not very tight or it doesn't fully expand, and you will get a smaller scale or larger scale because of the sensitivity of the contact point. Now, with the distance metric that we have, it addressed that problem.
Thank you very much.
Thanks.
Thank you. I saw you mentioned like people the wound like the weld. So imagine if you have a wireless one, maybe use some method like the Bluetooth low energy to send the signal in real time. Imagine, will this signal will affect the ECG or EOG stuff?
I think in order for you to capture the so first of all, without any way of canceling all the noise, that we would expect that you would see noise caused by those communication channel. As I show in one of the in our prototype, all the wire we need to seal the wire to make sure that it doesn't couple with the wireless signal. Now, for you to capture the wireless signal, you have an antenna, right? And the most dominant one here is the wire that serves as an antenna. And without sealing it, we actually can even pick up the AC current, right? So with sealing it, we reduce a lot of noise. And certainly, as long as you know the property of the signal of the noise, you can filter it out. And in our case, for the pre-processing, we do filter, and much of it are based on the prior knowledge about the kind of noise that you would be expecting.
Yeah. So do you mean if you know the channel you use to communicate, you can deduct the noise? So it's supposed to be work. If in another scenario to control the wheelchair, maybe a lot of noise around. So it's supposed to be noise reduced.
Yes, right. I think when you control the wheelchair, and I would worry more about the other electronic component that on the wheelchair itself than the wireless communication channel, because again, you have when the transmitter radiate, it is that channel is very well studied, and you know what kind of interference that would introduce to the system, right? So canceling that should not be a problem. Thank you. Thanks.